Welcome back to G Fun Facts Online. Today we are diving deep into the engine room of modern artificial intelligence to explore a paradox that defines our current technological era. It is a problem of scale. Over the last decade, we have effectively cracked the code on intelligence. We have built machines that can write poetry, diagnose diseases, and write code. But the solution we found is heavy. It is massive. Models like GPT-4, Claude, and Gemini possess billions and sometimes trillions of parameters. These are computational leviathans. They require warehouse-sized data centers, consuming rivers of electricity and water to function. Yet, the world does not just demand intelligence in the cloud. The world demands intelligence that is light, fast, and local. We need AI that lives on a smartphone, inside a robotic arm, or embedded in a medical sensor deep within the human body. So how do we bridge the gap between the God mode capability of a massive supercomputer and the constrained reality of an edge device? The answer lies in a technique called knowledge distillation. This is the pedagogical science of machines teaching machines. It is the unsung hero behind almost every real-time AI application you use today, and it challenges the very notion that bigger is always better. To understand knowledge distillation, we have to go back to the genesis of the idea and look at what a neural network actually learns. We need to hunt for what researchers call dark knowledge. When we train a massive deep learning model, let us call it the teacher, to classify images, we typically judge it by its top prediction. If it sees a picture of a golden retriever and it says golden retriever, we call it a success. We pat the model on the head and move on. However, in 2015, Geoffrey Hinton, Oriol Vinyals, and Jeff Dean published a seminal paper titled Distilling the Knowledge in a Neural Network. This paper changed everything. They argued that the correct answer is actually the least interesting part of the model's output. Think about it this way. When a massive model analyzes an image of a golden retriever, its final output layer, known as the softmax, might assign a 90% probability to the label dog. But that leaves 10%. That remaining probability is scattered among other classes. Maybe it assigns 9% to wolf, 0.9% to cat, and 0.0001% to truck. In standard training, we ignore these small numbers. We treat them as noise or error. But Hinton argued that these small numbers are actually dark knowledge. They reveal how the model thinks. The fact that the model gave wolf a 9% probability and truck a near zero probability tells us something profound. It tells us that the model understands the morphology of the animal. It knows a dog looks like a wolf, but it does not look like a truck. This structural understanding, the relationships between the incorrect answers, is the essence of intelligence. Knowledge distillation is the process of forcing a smaller, compact network, called the student, to learn not just the correct answer, but these subtle, rich probability distributions produced by the teacher. Now you might be wondering, how do we mechanically transfer this IQ from a 100-layer giant to a 5-layer dwarf? The secret lies in a variable called temperature. In a standard softmax function, probabilities are often pushed to extremes, like 0.99 versus 0.01 to make a decisive prediction. This sharpness hides the dark knowledge. If the probability of wolf is 10 to the power of -5, the student model cannot learn from it because the gradient is just too small. Distillation introduces a temperature parameter to the softmax function. By raising the temperature, the probability distribution softens or flattens. The peak, which is dog, lowers, and the valleys, like wolf and cat, rise. This exposes the hidden relationships. In this setup, the teacher processes data at a high temperature, generating soft targets that reveal its reasoning. The student is then trained to minimize two errors simultaneously. First, the distillation loss, which is the difference between its soft predictions and the teacher's soft predictions. This makes the student mimic the thought process. Second, the student loss, which is the difference between its hard predictions and the actual ground truth. This ensures it still gets the right answer. This dual objective training creates a student that is significantly smarter than if it were trained alone on the same data. It effectively downloads the generalization capabilities of the teacher, bypassing the need for the massive dataset and compute power the teacher originally required. As the field evolved beyond 2015, researchers realized that simply mimicking the final output was not enough for complex tasks. This led to a rich taxonomy of distillation methods. The classic Hinton approach I just described is called response-based knowledge. It is simple and works remarkably well for classification. However, it treats the teacher as a black box, ignoring the internal features that led to the decision. This limitation gave rise to feature-based knowledge. If response-based distillation is teaching a student by showing them the answers, feature-based distillation is showing them the workings. Deep neural networks are hierarchical. Early layers detect edges, middle layers detect textures, and deep layers detect semantic objects like eyes, ears, and wheels. In feature-based distillation, pioneered by architectures like FitNets, the student is forced to align its intermediate feature maps with the teacher's. Since the student is smaller, its layers are often narrower. So researchers use projection layers, essentially one-by-one convolutions, to resize the student's feature maps to match the teacher's dimensions. This ensures the student sees the data the same way the teacher does at every stage of abstraction. Then there is the most abstract form, relation-based knowledge. Instead of mimicking specific outputs or features, the student mimics the relationships between data points. For example, if the teacher calculates that image A is more similar to image B than it is to image C, the student must learn a feature space where that geometric relationship holds true. This preserves the structural topology of the learned manifold, making it highly effective for tasks like face recognition and metric learning. Fast forward to the modern era, specifically between 2022 and 2025, and the explosion of generative AI shifted the focus of knowledge distillation from computer vision to natural language processing. Distilling large language models presents unique challenges. You cannot simply match probabilities when the output is an open-ended sequence of text. We also faced a new problem, the white box versus black box dilemma. In traditional distillation, you have access to the teacher's weights. But today, the best teachers, like GPT-4 or Claude 3.5, are often behind APIs. We cannot see their logics or hidden states. This constraint gave rise to data distillation or synthetic transfer. The process is fascinating. Step 1. You take a massive, unlabeled dataset. Step 2. You feed it to the teacher and ask it to generate labels, explanations, or what we call chain of thought reasoning. Step 3. You train a tiny model, like Llama 3 to 8B or Tiny Llama, on this synthetic, high-quality data. Chain of thought distillation is particularly powerful here. Instead of just outputting the answer 42, the teacher generates the logic. First, I divide by x, then add y, so the answer is 42. The student learns to mimic the reasoning steps, effectively compressing the teacher's logic into a smaller parameter count. This is exactly how models like Distilbert and Microsoft's Phi series achieve state-of-the-art performance with a fraction of the size. We also need to talk about how these models are trained, because it is not always a one-way street. There are three main regimes. First, there is offline distillation. This is the standard approach, where a teacher is pre-trained and frozen, and the student is trained later. It is resource-intensive, but reliable. Second, there is online distillation. Here, the teacher and student are trained simultaneously. This sounds counterintuitive. How can an untrained teacher teach? It turns out that in a deep mutual learning setup, two small peer networks teaching each other often outperform one large network. They push each other out of local minima. And finally, the strangest phenomenon of all, self-distillation. A model acts as its own teacher. You train a model, freeze it, and then use it to retrain a fresh version of itself. Empirical evidence suggests this acts as a powerful form of regularization, denoising the dataset and smoothing the decision boundary. So, where does the rubber meet the road? Knowledge distillation is applied everywhere. In mobile vision, Face ID systems and smartphone cameras use distilled models to process images in milliseconds without draining your battery. In autonomous driving, cars cannot tolerate the latency of sending video to the cloud. Distilled models running on edge hardware, like the NVIDIA Jetson, detect pedestrians and lane markers locally. In the world of IoT and tiny ML, distillation enables keyword spotting, like waiting for the phrase "Hey Siri," to run on chips with kilobits of RAM, always listening, but consuming microwatts of power. And in real-time translation, distilled transformers allow for on-device language translation, which is essential for privacy and offline functionality. Looking ahead to the trends of 2025, despite its success, knowledge distillation is not magic. The capacity gap is a real limit. If the student is too small, it simply lacks the neural circuitry to comprehend the teacher's complex patterns, leading to a collapse in performance. Current research is focusing on quantization-aware distillation. This involves combining distillation with 4-bit or 8-bit quantization to create models that are both structurally simple and numerically compressed. There is also cross-modal distillation, where a teacher trained on rich data, like video plus audio, teaches a student that only sees one modality, like audio only. The student learns to hallucinate the missing visual context, improving performance in blind environments. And finally, adversarial distillation, which uses generative adversarial networks to generate difficult synthetic examples that probe the student's weaknesses, forcing it to align more perfectly with the teacher. In conclusion, knowledge distillation challenges the notion that intelligence is strictly about the number of neurons. It proves that intelligence is about the density of information. By compressing the dark knowledge of digital giants into compact, efficient forms, we are democratizing AI, moving it from the server farm to the palm of our hands. As models continue to grow, the art of making them small will become just as important as the science of making them smart. Thank you for listening to Fun Facts Online. If you enjoyed this deep dive, make sure to check back for our next episode.